All right, so today we're jumping into a really cool type of AI. It's revolutionary because it doesn't just look at data points in isolation, it sees the connections between them. We're going to be talking about graph neural networks, and let me tell you, they are quietly changing the world by teaching computers the language of relationships.
So let's start with a really powerful real-world example. Imagine you're trying to discover a brand new medicine. For an AI to help, it's not enough to just know what atoms are in a molecule. It has to understand how they're bonded together, that complex three-dimensional structure. That structure, well, it's everything.
And that really gets us to the core question for this whole explainer, doesn't it? We can feed a computer a long list of facts, but how do we actually teach it to understand the complex web of connections that defines, well, everything from a molecule to your social circle? The answer, it turns out, starts with a really simple but profound idea. You have to see the world not just as a collection of individual things, but as a graph. So what in the world is a graph neural network, or a GNN for short? Well, to put it simply, it's a type of AI that's built from the ground up to handle data that looks like a network. It thinks in terms of nodes, which are just the individual points, and edges, which are the lines connecting them. And what's really wild is once you start looking for this structure, you see it everywhere. A molecule? That's a graph. The atoms are the nodes and the chemical bonds are the edges. A social network? You and I are the nodes and our friendship is the edge. Same thing for academic papers citing each other. Or computers on a network. The world is just full of graphs. Okay, so a GNN gets nodes and edges, big deal, right? But how does it actually learn from that structure? Well, that brings us to its secret weapon, something called message passing. This quote from the source material absolutely nails it. GNNs work because the nodes actually talk to each other. They keep updating what they know about themselves by passing information back and forth with their immediate neighbors in the network.
Let's break that down, because it's actually pretty intuitive. Think of it like gossip spreading through a town. First, a node gathers information. It listens to what all its direct friends are saying. Second, it processes all those little bits of gossip. And third, it updates its own opinion or status based on everything it just heard. This happens over and over again, allowing information to flow across the entire network.
This visual here really helps clarify that first step. See that red node in the middle? It's not learning in a vacuum. It's actively pulling in information, these messages, from all the blue nodes it's directly connected to. Its understanding of the whole graph is built from its local neighborhood, one step at a time. So, message passing is the key building block. But how does that build up into a full-blown neural network? Let's peek inside and look at the fundamental layers of a GNN's architecture.
So a typical GNN processes a graph in three main stages. It starts with the raw graph data, and then, layer by layer, the network builds a richer and richer understanding until it can finally make a prediction about the graph as a whole. Let's walk through each stage. The first stage is where all that message passing we just talked about happens. It's a special kind of layer that's permutation equivariant, which is really just a fancy way of saying the network doesn't care if you shuffle the nodes around. The important part is that each time you add one of these layers, every node gets to hear from neighbors one step further away. So, one layer, you hear from your friends. 2 layers, you start hearing from your friends' friends. Next up, you have local pooling. This is where the GNN starts to zoom out and see the bigger picture. It essentially summarizes groups of nodes into a single representative node. It's a really crucial step for understanding the overall structure, kind of like going from a street-level map to a satellite view. And finally, after all this message passing and pulling, the GNN needs to actually give us an answer. That's the job of the final layer, global pooling, or what's often called the readout layer. It takes this super complex representation of the whole graph and boils it down to one single output. That output can then be used for a specific task, like predicting, is this molecule a good drug candidate? Yes or no? Now, if you're familiar with AI that works on images, some of this might be ringing a bell. And this table right here is the big aha moment. A convolutional neural network, a CNN, is basically a GNN that's specialized for one very specific type of graph, a grid of pixels. In a CNN, each pixel is a node, and its edges are just its connections to the pixels right next to it. GNNs just take that incredibly powerful idea and generalize it to any kind of network. Okay, so this isn't just theory. Now that we have a feel for how GNNs work, let's look at the incredible superpowers they have in the real world.
I mean, the impact is absolutely staggering. GNNs are a core part of DeepMind's AlphaFold, which solved the 50-year-old grand challenge of protein folding. They're being used to discover new drugs, they're powering the recommendation engines on the social networks you use every day, and they're even sniffing out cyber attacks by spotting weird patterns in network traffic. They're even helping design the next generation of computer chips. It's amazing.
But, like any powerful technology, GNNs are not a magic bullet. To really get the full picture, we have to look at their limitations and the open questions that researchers are still trying to figure out.
One of the biggest challenges is this idea of expressiveness. In simple terms, it means there are some patterns and structures that GNNs are just, well, blind to. And this image shows the problem perfectly. To you and me, these two graphs are obviously different, but to a standard GNN that relies on this message-passing idea, they can look identical. The network literally can't tell them apart, which, as you can imagine, can be a huge problem for certain tasks. And researchers are tackling other really tough problems too. There's something called oversmoothing, where after too many rounds of message passing, all the nodes kind of start to look the same, losing their unique identity. There's oversquashing, which is like trying to shove all the information from a massive network through a tiny bottleneck. And heterophily, which is a fancy word for when connected nodes are actually very different from each other, which goes against the basic assumption of many GNNs.
This quote really highlights that we're on the cutting edge. The entire field is actively debating whether the future of GNNs is going to stick with this message passing idea we talked about, or if a completely new approach is needed to get past these hurdles. And that leaves us with a final, and I think really fascinating question. GNNs are, at their core, a tool for teaching computers to think in terms of connections. As we get better and better at modeling everything from our brains to our economies as these complex graphs, what new problems are we going to solve? What frontiers, once thought totally impossible, are we finally going to be able to explore?